We welcome on stage Hartmut Schultze, who will walk us through the path to the cure of Alzheimer disease.
Hello. I would like to introduce today to you the path to cure, and what is better than let the customer talk? If it works, it does. Is there sound?
At the moment in the US, there are about nearly 6 million people with dementia. In Germany, there are nearly 1.7 million. According to some estimates, if we would not stop the progression of dementia in the world population, by 2050, we would need the entire GDP of the US today to be able to take care of people with dementia. So it's a tremendous problem. Obviously, the number is increasing, and at the same time, we don't have medicines that at the moment can stop the progression of disease. So we need to be able to have different ways by which we can do analysis. And of course, we have to collect a lot of data. We need to be able to develop new technologies to put all together a library of genomic data or imaging data that can enable us to compare an individual who has come for an early problem to the same individuals 2 or 3 years later and try to be able to find matches or mismatches. At the moment, we're working in compartments. Some scientists are working on that one, some are working on the other one. To solve these diseases, you have to take the whole picture. That's why we came to collaborate with Hewlett-Packard Enterprise, because of the machine.
I was thrilled when I saw it, because it was exactly what we were looking for. When we looked at genomic data, we wanted to have something where you can store a lot of data in the memory. We would like to have a fast system in a decentralized fashion, so we could even work together with colleagues who would also have genomic data at other places in the world. What we would like to do is that where the data is produced, we can keep the privacy for the data. We have the raw data, and we analyze this raw data in a fashion that whatever gets out as metadata, which is much smaller, we can then transfer it for analysis, for sharing, and things like that. So everything we were looking for seemed to be in this project. It is fulfilling a lot of criteria in the medical field, much better than what we have at the moment.
We have already run some preliminary experiments, so processes which take 25 minutes have been reduced to 69 seconds. Let's say you now process genome from 1,000 people, then automatically you will have data in such a fast time it will enable the scientists to be able to find solutions much quicker.
Having the idea to reinvent computing to what we really need is the key. And I think companies like the Hewlett-Packard Enterprise, they can help us to accelerate medicine.
The human brain is complex in a normal physiological state, so the dysfunction of this complexity is even more challenging. We need to be able to improve our way to do science, and here it is where we hope that our collaboration with Hewlett-Packard Enterprise will bring a tremendous advance in the field.
So, what is the DZNE doing? The DZNE is a German federation-funded organization around Germany. It's 10 locations. It has 40 full professors, 80 PIs. Very respected in the overall science community worldwide. And now, starting 2009 until now, it has 1,200 people working on the disease. And as you heard Professor Nicotera, the CEO of the DZNE, saying, it is a societal problem we're trying to solve here, because if we don't stop this disease, we would not be able to pay for the cure or for caring for all those people. So if we don't go into that direction, and that's exactly the reason why the German legislation said, okay, we need to fund this and put money into this. And as you heard in the beginning, also our colleagues working on this, I'm pretty sure anybody of the audience here in the room has an example, unfortunately, of somebody who might have Alzheimer's disease. So this is something we really need to tackle. So what is it all about, what we are trying to do with this project? We have patients. We do high throughput gene sequencing, we have clinical data, we have imaging data, and laboratory data. And like you heard Dr. Go saying, concentrate on a focus. We need to spread this out again because we know since we don't have a cure for Alzheimer's as of today, we need to find the whole spread picture, and we need to take every discipline into consideration on finding then the right biomarkers which come out of the gene, which come out of imaging, which come out of clinical data. We do big data analysis, we do the models, the diagnostics, and we are looking for every single mean on how this information can help us. This will be going back into validation and then hopefully coming for us as a patient. So how does this look like? It is pretty fancy if we visit the DZNE by itself. It's a large institute in Bonn. So all these pictures are done in the wet labs, and what you see here is some sorters, there's some gene expression analysis apparatus. These machines were able, or probably heard of the first gene sequencing genome in 2000, something like that. It cost about 3 billion to do one single genome. Nowadays, we're there with 1,000 euros. So expect yourself to have a gene sequence in about 5 to 10 years for every visit you're going to for a doctor. On the other hand, you're going to generate about, like said in the video, 180 gigabytes for one single cell. So if we take a blood droplet from your body, do a gene sequence on this, it will take about 180 gigabytes where we will try to extract data out of it to find a biomarker which might lead to the disease. So looking at the overall picture, we have a lot of different disciplines. It's the genome by itself. There's an RNA analysis like transcriptomes, epigenomes, microbiomes, imaging, clinical epidemiology data, nutrition data, also how you interact with your friends, for example, because one reason to maybe hinder also your progression of the disease is if you talk with friends. So this is, for example, very important that you go out and talk to people. It's very bad for people just to be alone somewhere else in their own homes. They need to participate in their culture and in their society. We don't know the exact thing as of today. We would like to put everything together in the systems medicine approach, and of course computing is central to this. And this is how we came together, to have the overall picture of the broad information we have. And you can imagine, as said, about 180 gigabyte per one single cell for each person. The DZNE is going to do a study with these up to 30,000 patients over a period of the next 30 years. We're thinking about having something like 500 petabytes to 2 exabytes we would need to analyze in combination. So if we only do one part, it doesn't help us. It's right to focus, like Dr. Go said. On the other hand, we need to broaden our picture again to all our information we have. So this is where we came to memory-driven computing. And like I like to say is memory matters, not only with Alzheimer's, but also how we do approach these problems. So I give you just a small picture on what is it all about. You've probably seen this picture. So this is a small representation of the von Neumann structure. You have a CPU on the one side, you have the DRAM attached to it. All the communication goes via the DRAM into a network where you have your storage and have your data persisted, what you would like to analyze. So this principle we are trying to put together. So just combining DRAM and storage to have one shared memory pool. And the interesting thing is, you in your brain, you do the same thing. You have one brain. You don't have many brains. and many neurons are firing, and that in a way which is much slower than a computer does it right now, but much more efficient. And the same approach we're trying to get here with our memory-driven computing. So try to get the information in one single point and get all the information together. So our goal is to have in the future our 2 exabyte of data we would like to analyze in this study, analyzed in combination in one single memory. So we are coming from a structure where we have a network, like it's in every supercomputer, where you do a lot of messaging, you do a lot of communication. And maybe there's one picture you can compare to if you're in an office. And this is how you can see memory-driven computing, is if you're in an office, you have a lot of different small offices. And if you want to have one information, you step out of the room, go into the next office, get the information, go back. Then you have a travel time, you need to get the information and put it into another bucket. If you go on the other side and say, have everything in a single dedicated space in an open room where everybody can access it, and everybody can immediately draw some information out of the data you have, then you come to a structure which is like going from a distributed office-based into a central space, but this central space does not have to be locally. So not everything needs to go into a data center or something, because on the other hand, you need to have it distributed. I'll give you one example. These 10 locations do genome analysis, and in every single center, a genome is taken. And of course, as you would probably agree, is that the genome by itself is the most private data we have as of today, because you can be identified by your genome, by a single hair, by a single cell, by a blood droplet, by some skin you have. So this is something which should not leave anything else, but the doctor or the hospital where you trust it to be there. So we need to have a structure where we can analyze the data overall, which is distributed, but thinking of it having the complete access immediately at once also. So from a perspective of a computer by itself, if you see on the left side, every communication now depicted in this graphic is that everything is going through the CPU as of today. So the CPU does all the communication handling. What we are going to do for the future, though, is we're going into a fabric-based. So we have accelerators to it, we have DRAM to it, we have memory components to it, and we have also compute components to it. This is a change from the current structure. As we see, everything is data-driven. We need to put our memory into the center of our thoughts. If I go into the one use case where we started, so it's the simple thing. You have a person, you take a blood droplet, and you do a genome expression on it. And we tried to find out if it was possible to accelerate this by using the principles of in-memory compute, data-driven computing, memory compute. So we went exactly to that portion and said, okay, if we can accelerate for the pre-processing step, where we do this analysis, we could probably accelerate the overall picture for different disciplines in different areas. And in our first use case, we took the near-optimal RNA sequencing quantification algorithm, which was published in 2016 by the Pachter Lab from Berkeley. And they said, okay, we can analyze a data in 22 minutes. These 22 minutes, we put on a large memory machine where we mimicked the principles we would like to apply. And then we found we can approach it differently. We don't move data around anymore, but we move pointers instead of data. We optimized the way on how the quantification algorithm by itself worked, and we found that we could improve it to 13 seconds. Now, what I just told you, in 2000, we had about one genome analyzed. It took 3 billion in cost. Now it's 1,000 euros. We're seeing it's going to 100 euros. We come from a week of analysis to 13 seconds. And this is going to just accelerate. Now we're even talking about and implementing this now to change the format and how we do these analysis steps. As you can imagine, a data pipeline, which we have there, is really long. It is complicated. And a lot of scientists are working on this. Now we're changing on how to communicate through memory. The thing what I would like to tell you, though, is the principle is completely easy. On the left side, you have a stack, how we do this as of today. We have a lot of communication going into it, and instead we're moving everything in a single persistent or volatile memory base where everybody can access this. This is the principle. So it's nothing complicated, but you have to change on how to approach this. So what is it all about? Think of memory-driven computing, of having unlimited, ubiquitous memory, and think of being able to access all this memory at once, even if it's distributed. And I give you one number for one of the technologies we have behind here, which was then coming out of the machine research project, and this is now going into our products, is one specification of a consortium in the industry, which is Gen Z, which is spreading nodes, and you can access a memory space of 4,096 yottabytes. And yottabytes is about, this size is about, as of today, roughly about 100,000 times the data which exists on this planet. So all this data you could put in one single computer. And as a person asked me one time, well, would it be possible then to download all the data we have on the internet into one single computer? Yes, in principle, yes, it's possible. But of course, we wouldn't do it because the transmission of the data is just not possible. It's just too much, so we don't do that. Nevertheless, don't let yourself limited by any border you have been given and saying, okay, well, I cannot access and analyze an amount of data which is so large, it's just not possible. So if you take one thing, and that's what I would ask you, if you take one thing out of this room as of today, don't let yourself limit yourself by having not enough memory, because that's possible. I'll give you one other example. I was at a travel company, and they had a big data problem. They have something like 1,000 servers analyzing data and then also preparing information for researches on how you do your travel. So every time you do your travel research, you send a request to a server, and then it gets loaded from a database. And then I asked them, okay, why do you use 1,000 servers? And they said, well, we need to have that because we have the structure that we have, the requests must be fast. And I asked them, okay, how big is your data set? The first question was, well, actually, we don't know right now. So it was only the structure in place because they said, well, we have a lot of data, so we need to spread it out to a lot of computers. A couple of weeks later, they came back and said, okay, we have a data set which is about the size of 10 terabytes. I said, okay, well, this is as of now, as of today, a limit which we can easily reach. So we have the technology available right now to go to at least a 50 terabyte in memory. As of today, maybe not at the cost point we would like to have in the future, but it's exactly the same. As I told you, 500 petabyte to 2 exabyte we would like to do in the study of the DZNE over the next 30 years. It's possible to have all this data in one persisted memory pool. And of course, then you change on how to do the analysis. So you can imagine streaming data coming in from a genome center, streaming data coming in from a MRI, from all these sources I have, and on top of that, we are going to learn and find out what are the biomarkers to get a possibility to cure this deadly disease of Alzheimer's. This is the thing we are going to have in the future. So what is it? Classical versus memory computing is today's architecture. Pretty much every single computer does it like this. It's trapped. Everything needs to go through the CPU. And what I've shown you from the analysis and the results we got there, which are going to be published in Nature, is that a lot of those and 60% of the memory we can reduce is based on communication needs through the CPU. Of course, we need to find every single measure and every possibility and every technology to improve the way on how we do this. On memory-driven computing, the data is central, so it's data-driven. Everything is data-driven, and we circle around all our infrastructure, even if it's new accelerators, specialized chips, analysis engines to access our data, which we would like to analyze in the future. Coming to this, it's going to be right-sized in real time. So think about memory processors, accelerators coming together and as we see and hopefully are hearing as in the other talks as well, that we have an array of logic devices. These logic devices doing specialized tasks, very focused. On the other hand, thinking about the large picture, always the large picture. The components are then interconnected via very fast interconnect, which is mostly, or that's what I expect, to be based on the fabric. It's a fiber because that's the mean where we have the lowest loss. And then we can implement these in different devices. This could be an edge device, a small device, and you do a mix and match of all those components coming together. This can even go into the exascale arena. So in the exascale region, which is probably not the industry you're currently thinking of, you have a lot of components. So the supercomputer of tomorrow is going to be built on something like these technologies, and I'm absolutely sure for this. As you heard, we were acquiring Cray computers. This is just about to come. It was just approved, and all these technologies come together. Nevertheless, we will see a lot of data space where we can then all put these technologies together. How big? I told you the one number, 2 to the power of 92, which would be one single computer, but we can connect a lot of these devices together. So any problem you are going to have, and you think of being limited by the number of memory you need to access for those things, I can tell you, or I would promise you that in the future this boundary is not there. And therefore, think just differently. Just try to think differently. What we did so far is, for example, in Spark, in-memory analytics on a single node, We could improve by changing something like 300 line items of code on a factor of 15. In genomics, like you saw, it's in the range of 100 or 112. In large-scale interference, so graph analysis, it's also a factor of 100. So, and in financial models, if you just have a different approach, for example, like if you take the curves, like Dr. Go just said, 50 days or 200 days, if you put all the different paths into memory and just do a lookup afterwards, you come to a region of 10,000x. So you get immediately faster. So thinking about pre-processing things and then do a lookup. The interesting thing with gene and expression analysis is it's exactly the same. You have a long string of information, you put this information somewhere, and what we saw is that if we increase the size of an index without shuffling data in between, we could improve this by a factor of 10, only because we did the index differently. Why could we do it? Because we had an ubiquitous memory space. Memory is everything, memory matters, and this is the way on how we try to get the path to a cure for Alzheimer's disease. It's not there yet. The scientists still do not know exactly what has to be done in the future to prevent this deadly disease, which is going to be, unfortunately, relevant for everybody in our society. Nevertheless, this is the path on what we're working on together with the DZNE. Thank you very much.